Okay, so far we've looked at linearity and we have looked at superposition. Superposition derives straight from linearity, so you can only apply superposition to linear systems or linear circuits in our context. And now we're going to look at source transformation. Source transformation is more of a tool, a technique, than it is a theorem, though it will come up again when we look at two other important theorems, Thevenin theorem and the Norton theorem. And those two will be related actually through source transformation, as will become apparent. So we're going to begin with a single voltage source and resistor. Call it V, S1, and R1. And we're going to label this voltage here V and I, and then we're going to connect a load. And we could either connect a resistor or we could connect a voltage source, or sometimes I'll use the word, did I say voltage source? I meant current source. Actually here I'm going to call it a current sink. Okay, now current sink and a current source are really the same thing, other than that there's implied in a current sink that the device is, or the source is actually acting more as a, not a source of energy, but a sink of energy. It actually is absorbing energy. Be that as it may, you can just treat this as a current source. I'm going to call it IL. This is kind of like our load. Okay, we'll say this is like a load that is connected to the source. Now you could think of VS1 and R1, maybe it's like a battery, like a realistic battery that has an internal voltage and then internal resistance to it. But what we're interested here is to answer the question, what happens to the voltage V? Okay, so that would be if this was treated as a battery. Okay, a battery. Then what would the output of this real battery be, output voltage be, as we start demanding some current from it? See, I is directed to the right, and if this were a battery on the left, then that current is actually the current the battery would supply to the load. And we're going to use a current source to behave like our load, okay? And we'll start off by looking at when the current is 0. So if there's no current flowing, so I program IL to be 0. Okay, this I is equal to IL, right? If IL is equal to 0, there's no current flowing. There's no voltage drop across R1 then, right? And so the voltage V is simply going to be equal to VS1. Okay. Let's actually write an expression for V in terms of VS1. And what we're going to do is, you can solve this by KVL. If I walk around this loop and you add all the voltages, we could come up with an expression. I'm going to venture to say that at this point you're going to be comfortable with me simply writing this by inspection and saying that this voltage V from plus to minus here is going to be equal to VS1, okay, plus whatever voltage is dropped across the resistor VR1. Okay, so we'll have VS1 minus, because the polarity is plus to minus here, minus R1 times I. Well, I or IL. Okay, that's the equation of a straight line, and it in fact does have a y-intercept at VS1, and it has a slope of minus R1. And we will draw a straight line here, and it will cross at some, it'll cross the horizontal axis at some current I, and I'm going to call it ISC. The slope of this line, as I mentioned, is going to be minus R1, the open circuit voltage, open circuit meaning there's no IL, there's nothing connected to the load, no load connected, will be Vs1. And at the point that the curve crosses the x-axis, we have a voltage across our load of 0. Okay, so what we term this current point to be here, where the line crosses the y-axis, we call it the short circuit current, because it is the current that results when you short the load, the output. Okay, so if we're taking, again, think of this as a battery. We short the battery, how much current flows? It's the short circuit current. And that current is going to be equal to, if I just, I mean, I think you can see what it is, but let me draw what that circuit will be when it's shorted. We just have our Vs1 and R1, and the short circuit current ISC will just be V over R. Okay, Vs1 over R. So for example, if we have a battery that is a 12 volt battery and we have R1 equal to 0.1 ohms, then the short circuit current would be equal to 12 volts over 0.1 ohms, or 120 amps. And we would have this voltage versus current plot that would look like this. It would have a y-intercept of 12 volts and an x-intercept of 120 amps, and it would have a slope of minus 0.1 volts per amp. And what we call this curve is, let me get another color just to make it interesting. We call this the batteries, in this case if this is a battery, okay, the battery's load line. Okay, we call it a load line. So you think this line predicts or shows what the load will see in terms of voltage V as the load demands a current I, or if the load is is a type of load that demands a current, like this current sink, then the load line says what voltage the load will see in response to a particular current demand. Or I think that's what I just said. So it could be the other way around. If the load is acting more like a voltage, controlling the voltage, then the load line says what kind of current the load will experience for every particular voltage that it would force upon the source, in this case the battery. Okay, so now I haven't said anything about source transformation yet. Let me draw another circuit. This time it's going to be a current source. I'll call it IS2, and we'll have a resistor R2, and again we're going to connect a load. We'll call this V and I again. Okay. Now we want to create the same load line for this type of source. All right, and we have V and we have I. And now, if we short the load, so in other words, if V is equal to 0, so the short circuit condition now is going to be this. And this short circuit current flows through that short. What is the current going to be? Well, you have a current divider between R2 and the short. but the short has zero resistance, infinite conductivity. So all of the current source IS2 is going to flow through the short circuit path. And so we will have, down here, we'll have an I short circuit equal to IS2. Now what if we do an open circuit? Open circuit would be when there is no current path out to the load. And now we have the following circuit, and the voltage that we would see would simply be IS2 times R2. So V open circuit, I should have called this V open circuit up here, okay, is going to be equal to R2 times IS2. And again, it'll be a straight line with the slope of minus R2. Okay, so now the question is, both of these sources, the voltage source VS1 plus R1 and the current, the other source IS2 with R2, both produce a load line that look identical. I mean, at least in shape, right? Let me write actually an expression for this. We never wrote the expression. We would say that V is equal to IS, I'm going to do KCL at this node here, right? Oh, not there, up here, KCL. So we'll have IS2 minus IL times R2, which is equal to IS2 R2 minus R2 IL. And this has the same form as, where's my other expression? I've lost it. Oh, right here. So we have one right here, and now we have the second one right here. They're both a voltage minus the resistance R1 or R2 times the load. So can we equate those two? Could we actually force these two sources to have the same load line? All right, and the answer is yes, we can. So let's make the two sources, and when I say sources, I mean the source and the ideal source and the resistor, have the same load line. How do we do that? We would say that we have V is equal to VS1 minus R1 times I load. That's what we had for the first one. That has to be equal to R2 IS2 minus R2 IL. Well, that's easy. We then just specify that R1 must be equal to R2. That'll get our second term. And that VS1 will be equal to IS2 times R2. Okay. So this is actually really easy to carry out. Let me show you. So suppose that we have a source it's 5 volts and we have a resistance that's 2 ohms, and we want to drive an equivalent source that has the same load line but that uses a current source. How do we do it? Well, here in the first thing we do is we'd say, oh, this resistor must be 2 ohms because here we have R1 is equal to R2. Then secondly, I'm going to solve here for IS2, as a function of Vs1, okay? So because we're given a voltage source, okay, we need to find a current source. So this current source is going to be nothing more than the voltage divided by the resistance, R2, which is the same as R1. So this is nothing more than 5 volts over 2 ohms, or 2.5 amps. Now what's the power of this? The power of it is that at these terminals, okay, if I draw a box around this source and this source here, okay, if we put those in a black box, if you simply look at the current that's coming out, or that you're drawing out, and the voltage across those two terminals, you would not be able to distinguish whether you had the first circuit or the second circuit. In fact, we'll find out very soon that there would be an infinite number of circuits that could be inside that dashed box, which would yield the same load line. The load line in this case is going to be, 5 volts on the y-intercept and 2.5 amps on the x-intercept. And that's enough to actually specify this, but we can go ahead and add the slope as well. So you notice that the open circuit voltage, the resistance, and the short circuit current all make up what our source is. Okay, but actually only 2 of these are independent. In other words, if the open circuit voltage and the resistance are specified or are known, then the short circuit current is just VOC over R. And if the short circuit current and R are known, then V open circuit is just R times ISC. And finally, if we were actually just given V open circuit and I short circuit, then we would say that R is simply equal to V open circuit divided by I short circuit. In other words, only 2 of the 3 are needed to uniquely specify our load. And the powerful thing about this is that you can employ this to make circuit analysis more simple. Let's take a look at the example that we worked when we introduced superposition. This circuit right here. We will solve it using source transformation. So we're asked to solve for V1. In this case, we're going to use source transformation. Now, before we dive in, let's think about what might be helpful. We notice that if I put a dotted line through the middle here, to the left I have a voltage source with a resistor, to the right I have a current source with a resistor. I could source transform the left side from a voltage source and resistor to a current source and resistor, and that would I would end up with 2 current sources and 2 resistors. All of them would be in parallel. It would be a single node circuit. Single node pair circuit, excuse me. I could also source transform the right side from being a current source, IS2 and R2 resistor, into a voltage source with the resistor in series. That would lead to a single loop circuit. Okay. Now, if we were asked to just find the current flowing through R1 here, then I'll ask the question, which would you rather transform into? Would you like to do a transformation to result in a single node pair circuit or a single loop circuit? Well, I would argue you would want a single loop circuit, because once you transform this right side into a resistor and a voltage source, the single loop that would result would have a current that would be this current IR1. And by solving that single loop circuit, which is done very easily, right? Just sum the voltages, the independent sources, divided by the total resistance, and you get the current. So going to a single loop circuit would be the thing to do if you are looking to find the current. But if you want to find the voltage, which is what we're after here, you're better off putting it into a single node pair. And so that's what we're going to do here. We're going to do a source transformation on the left side, and we're going to replace that voltage source VS1 with the current source and a paralleled R1. Now I write R1 here because remember, when we do source transformation from the current to the voltage source or vice versa, the resistors stay the same. The only thing that changes is the value of the source. The source here for this current will be VS1 over R1. Now I draw the rest of the circuit, which is R2, and my current source, IS2, and the voltage V. I'm going to ground this. And now I simply have, really this is just Ohm's law. V is going to be equal to R times I, where R is going to be the parallel combination of R1 and R2, and I, in this case, is IS2 plus VS1 over R1. And if you expand this, you're going to find that this is the same answer that we arrived at by using superposition. So this leaves you with maybe a good feeling or a bad feeling, or a little of both. The good feeling is that, wow, I was able to simplify a circuit to a single node pair or single loop by using this, pretty straightforward transformation. The not so good feeling may be that you saw that we could solve the circuit using nodal analysis, which we did in the previous superposition lesson. We could solve it using superposition, which we did in the previous lesson, and now we just solved it by source transformation. And so you see there are many different ways that one can legitimately solve a circuit, and that may leave you feeling some freedom, or you may feel some worry because there seems like too many degrees of freedom. But that's the reality with engineering. When you go to solve something, and we're not even talking design yet, right? But I guess you could think of solving the problem as you're going to design the way you're going to solve this problem. That's your design problem. There's always more than one solution, one path to the solution. And as an engineer, a lot of practice and experience will guide you in kind of forming kind of some judgment on, given a certain problem or a certain system, how to best use the tools that you've been equipped with to solve or answer the question that's at hand in the most efficient way. And that's also what makes engineering very fun. So hopefully this is good news at the end, and not just giving some worry because now there's more tools and more options for solving a circuit. But be that as it may, we're not done. We're going to introduce Thevenin and Norton theorem next.